So yeah, we have done this automata we have done in Python, and now we have this ambitious project to do regular expressions in Python, which is quite a useful little exercise because running regular expression is actually like grep, the unix command which we have mentioned, is sort of a useful application. We have done deterministic finite automata, DFAs and NFAs, and we have looked at translations in both directions, and we've done this in Python, beautiful enough. And then last session we looked at regular expressions, and we have just done them on paper. And now today we're going to do them in Python. Okay, let's not look at the definition of regular expression, which is here. So let's not look at it, yeah. But let's look at an example. Here's an example regular expression, which is sort of our running example. So what's the idea? So it starts with b plus epsilon, so b or nothing. And then there is a sequence of a, b's, and then there is an a or nothing. And basically what this is, it's a sequence of a's and b's always interchanging. Yeah? I mean, you can have just an a, you can have also nothing, it's also okay. So these are the words, this is the language of this regular expression. So now the first question is, how do we represent a regular expression? What is a regular expression? So what's an expression actually? So we've done a video about this, on arithmetic expressions, and there are trees. If I turn this regular expression into a tree, that's what I get. Yeah, I wrote append for the sort of invisible, just one after the other, which is make explicit here. I call it append. Then there is this plus star operation, and down there are epsilons and symbols. And so this tree is a representation of a regular expression. Now we have to turn this tree into a Python object. So I'm going to define Python classes, and since this is a bit much, I already prepared this. Like, you know, if you have these chefs cooking something, they prepare some sauces. So I have lots of prepared sauces today because the recipe today is a little bit involved, let's say. Okay, so here I have defined a class of regular expression, which is an abstract class. So I'm not giving a way to create a regular expression, but I have subclasses, and each of these subclasses correspond to one way of making regular expression. Like empty is the empty regular expression. Epsilon, we have seen, is the one which is just the empty word. Symbol is one symbol. Plus, we have also seen append and star. These are the ways to make regular expressions. And I also have some boilerplate. Every regular expression can print itself. Okay, and now here I have typed in this tree as a Python code. Let me just run this. And now I have E1. So E1 is a regular expression, and it can actually print itself, as we can see. Okay, cool. So we have a representation of regular expressions, but what can we do with it? We want to run it. I want to have a run function. Yeah, here I want for every regular expression, I want to have a run function, right? So I want to have run, and it gets a word, and it returns true or false. So it returns a boolean. Yeah. So if this word is an element of the regular expression, I mean of the language, should say yes, otherwise it no. Now there's a little extra thing we have to supply. We have to supply the alphabet because that's an extra parameter. So we want to implement this run function. Now what's the idea? So if you look at this picture again, then I indicated that actually regular expressions and NFA have a close relationship. In particular, there is a translation from regular expressions to NFA, to non-deterministic finite automata. And we have already defined a run function for NFAs. So let's have a quick look at NFAs again. We want to implement the run function for regular expression, piggybacking on the run function for NFAs, which we have already defined. Okay, let's have a look at the NFAs. So that's what we have done previously. This is very simple. An NFA has a set of state, an alphabet, a transition function, set of initial states, set of final states. And we have a run function which, getting a word, sort of keeps track of the states in which the NFA could be. And at the end, it checks whether the set of states in the final states have a non-empty intersection. This AND here is actually the intersection operator from set theory. Okay, we have two example finite automata. So that's N0. This was the automata that recognizes that the symbol before the last symbol is 1. Okay, this is N0. I have defined it here. So that's basically hacking in this diagram as a definition of an expression. So I can do this N0.run and then 110, let's say, and hopefully it says yes. It says yes. Okay, that's already enough. And this, I have another finite automaton which I call N1, and N1 recognizes whether the last symbol is a 1. So it has here 0, 1, it stays in 0, but as soon as the last symbol is a 1, it goes in here, and that's this. I hacked this in as N1. Okay, this is two examples of finite automaton which we're going to use in a minute. So now back to our regular expressions. So we want to define this run function. What we're going to implement is this translation. I'm going to implement a method NFA, which gets the alphabet, and returns an NFA. So it returns a non-deterministic finite automaton which corresponds to this regular expression. So that's the idea. And once we have this, we can implement this run function, which gets the alphabet and the word, and it returns. Okay, return, not red run. Red run is not right. Okay, it returns. It converts itself to an NFA and then runs this on the word. Okay, so it's still red run. And now again, it boils down to implement this NFA function. So in the spirit of test-driven development, I'm going to write some unit tests. So I'm first of all write a test function which, given a regular expression and a word, and now we fix sigma, it prints the expression, it prints the word, and then it runs the expression on the word and tells you true or false. And we do some tests for this A-B example. Maybe we should also have a negative test. Okay. So for example, the empty word should be in it, A-B should be in it, A-B-B should be not in it, A-B-A, yes. B-A-B-A-B is also fine, whereas B-A-B-A-A-B should be not fine, okay? So that's our test suite, right? So how are we going to implement? So I'm not going to go all the details. Let's just look at some examples. Okay, so let's look at 3 examples. The empty regular, oh, yes, that's too small. The empty regular expression, the epsilon, and the symbol. Now, I have implemented the NFA method, which constructs the corresponding NFA. But to do this, I need to implement some factories which produce the non-deterministic finite automaton, the NFAs corresponding to it. Okay, let's look at these factories. I need a factory for the empty NFA. So maybe I can draw this. What is the NFA recognizes the empty language? There it is. Yeah?
That's definitely an empty language.
Yeah, it's the empty NFA, but the empty NFA recognizes the empty language. Yeah?
Okay.
And so here, when I do this in Python, I say out the empty set of states is the empty transition function, the empty set of initial states, the empty set of final states. That's the empty NFA. Very, very easy. So now epsilon. What's the epsilon? Okay, let me draw some pictures. So here, this is the NFA for the empty language, intentionally left empty. Now we have this epsilon. So this is a little bit more complicated. It has got one state, which is initial and final. So we start here. If nothing comes, we say yes. If something comes, we lose it, okay? So here also exactly this implementation in Python. We say, okay, there is one state, there are no transitions, the initial state and the final state is just this. Okay, and now the symbol. Now we have one symbol and we want to define an NFA which recognizes exactly this symbol. So how do we do this? We have actually two states, initial state and the final state, and we have one transition. And that is the regular expression A. So here I do this. We have two states. We have sigma as we get it. And we have one transition from 0 with sim. We have just one consequence, one next state, which is the state 1. The 0 is the only initial state, 1 is the final state. That's actually the translation. So let's look at this from the point of view of regular expression. So now I'm calling these factories. Now I have to say this is a class method. So I have to say this nfa.empty, nfa.epsilon, and whatever nfa.symbol. Okay, so we have this unit test. Yeah, the empty doesn't even recognize the empty word. The epsilon one recognizes the empty word, but not the word a. The a symbol doesn't say false for the empty string, but says true for a. It's just as expected. Okay, so now we get to the more interesting ones. So let me do this plus in some detail. Yeah, so we have to define a factory which gets two automaton, builds a new one, which recognizes the union of the language. Yeah, so it's like an order. We have to implement this plus. And it turns out, on paper, it's very simple. So how do we construct the plus of two automaton, or the automaton which recognizes a word from either language? Let's see, I have here n0, one automaton, here n1, another automaton, and all I do is put it together. So here, these two, I'm just putting them together. I have one bigger automaton. And this automaton will recognize a word either from this language or from this language. Okay, okay, so let's do the factory for plus. Here is a little bit of subtlety, because if you look at this automaton, so we want to define this plus, the factory plus. Gives two automata, call them A0 and A1, or maybe I call them A1 and A2. And now I need to construct the states of the union automaton. And the question is, how do I do this? So I have N0 has got some states, 0, 1, 2, and N1 has some states. So how can we put two sets together? Now what's the wrong answer?
Union. That's the wrong answer.
That's the wrong answer. So why is it the wrong answer? Because N0.Q union, which is a bar, N1Q is 0, 1, 2, is a union. But if you look at this picture here, we have 5 states, not 3. And if we combine this automaton and overlap these states, maybe in this example it works, in general it will not work, because we get into some chaos. Yeah? So there is some unintended interaction between these automaton. So I need what's called the disjoint union. Let me just run this. And I have implemented it myself, but it's not very difficult. So I have implemented a method dUnion. So I can now take the disjoint union of two sets. Let's just n0q and 1.q. And what it is doing, it labels the one from the first set with a false, and it labels the element of the second set with a true, and then puts them together. And this makes sure that they're kept separate. Yeah? So this disjoint union operator is what I then use. So I have prepared this already. Okay. So here, okay, for the alphabets I take the normal union, but for the states I take the disjoint union. And then I have implemented a little method which can also lift the function, the delta, to the disjoint union. Yeah? And then initial states, final states are the disjoint union, and I get a new automaton. And so I can now, for example, I can do NFA plus of two automaton, okay, in 0 and N1. And I get a complicated new automaton which if you look in detail is really a representation of this very simple action, putting two pictures together. But we have to take care that everything is kept separate. So I can now implement the NFA method for plus using the plus factory. And here there is, scary thing going on. There's some recursion going on. Because to translate a plus regular expression, I now have to recursively translate the subtrees and then plus them together. I test plus epsilon a. So let's see whether this works. So the unit test for plus. So if you have a plus epsilon, we recognize both the a and the empty word, but we still don't recognize a b. Seems to work. Okay. So let's tell the rest of the story. We have two more constructors, two more subclasses here, append and star. And for each of them, we have to find a factory. Now I'm going to give you the code. I will just show how it works. So I have to implement a factory for append and a factory for star. Now let me do this at least on paper. How do I do a factory for append? So I have one automaton for the first bit. Let's call it n1. And I have one automaton for the second bit, n2. And I want to run one after the other. So first of all, I put them together, like for plus. I just put a big thing around them, I put them together. But I only add the initial state for the first and the final state for the second. And then here, if here is a final state of the first automaton, and here is an initial state of the second, I'm adding what's called an epsilon transition. I can silently go from the end of the first to the beginning of the second. So this is n1, n2, just one after the other. And if you look at this implementation here, there are a few things to comment on, but what I'm basically doing is I put these two together, then I add the injection of the first set as initial state and the injection of the final state of the second as a final state, and then I say for any final state in the first and for any initial state of the second, add an epsilon transition. And here I have a little method of what it means to add epsilon transitions to an NFA. And star is actually not very different. So you have an NFA, you just take it, so this gets n, and now we have n star. And what we do is we first of all add the empty language, so that we, not the language, there's the empty word. And then we have to shortcut here from epsilon transition from the final states to the initial states. So we add all these lots of extra transitions. It's like we can go around as many times as we like. And that's this few lines of code here, and also adding an epsilon transition. And now going back to the regular expressions. Okay, let me go to my last prepared source. So now I have this factory for plus, the factory for append. I'm using here for append, also recursively translating the expression. And for star, I recursively translate the expression and then use my star factory. And okay, I have the wrong test, so that's very bad. How did this happen? Okay, let's go to here. Let's copy the unit tests over, which I wanted to do. And let's hope it works. Okay, let's see. So here, okay, oh, that's wrong. It didn't work. No, that's a nice thing. So here I checked the unit test, and the unit test doesn't work. It says false for BA, BA, B. And then I realized it's maybe not my code. I have the wrong test example, which I had before. Let me just copy it from here. Yeah, because that's also the wrong one. Oh, okay, that's the wrong one everywhere. Okay. So it's B plus epsilon. Yeah, and it finishes with A, otherwise it's wrong. And now I have to change this with B. And this was A. This is the problem. If you do test-based developments, your test should be right. That's an interesting bug. Test failed. Okay, this time it seems to work. So we have this complicated expression, and what do we say? We say the empty word is true, the A is true, AB is true, ABB is false, ABA is true, BABAB is true, and BABAAB is false. So seems to work. So now for entertainment, yeah, I asked what's the language of this regular expression, and now we can resolve the mystery a little bit, and at least we can play around with it. So I have here implemented this expression as a tree, as a Python expression, and now I can run it. So it says yes for 1, 1, it says false for 1, 0, 0, it says also false for 1, 0, 1, but it says yes for 1, 1, 0, and it says yes for 1, 0, 0, 0, 0, 1. Okay.
Starts and ends at 1?
Oh no, okay. Everything which ends with 1, you think. Okay, let's see whether that certainly seems to be justified by so far. But if you just add 1, then it should recognize 1, right?
Yeah.
Well, it doesn't.
Okay. Go on then, that's me. Go
Yeah.
if we need more info.
Yeah, we leave it. I mean, I'm going to I'm going to publish this code, and then everybody can play around and figure out what is the language. I mean, there's some binary numbers here, right? Maybe it has something to do with binary numbers. There's some property of binary numbers which correspond to this regular expression. Okay.
There's a few important properties of hash functions that we care about for cryptography, but the most important one perhaps is that it's essentially pseudo-random. So that means that we put in ABC.
The literal adding and incrementing and decrementing these counts can become surprisingly punishing in terms of performance.